So thank you for inviting me. And so you already introduced me. So I'm a climate scientist, but I'm also the director of an interdisciplinary center called Energy for Climate, which really makes the link between, let's say, climate variability and change and energy transition in general. And here I will focus my presentation on energy planning. So I will first start by making clear, if necessary, of course, but the link between climate change and energy. So the climate is warming up, so the observations speak for themselves. And here the figure shows the evolution of anomalies of surface temperatures compared to pre-industrial levels, average of the globe until the year 2000. And so the black curves shows the observation, and we see that first cooler years follow warmer years and vice versa. So this is called natural variability. But we see on top of the natural variability a significant trend showing evidence of a global warming that has accelerated since the 1980s. And so today, the climate has warmed by about 1.25 degrees Celsius, the latest figures issued by our colleagues of NASA. So compared to pre-industrial levels, and well, no doubt persists by emitting greenhouse gas concentration in the atmosphere. The man is responsible for this warming. So first, how are we sure that humans are the cause of global warming? And so for this, we use climate models. And so the red here and the blue curves are derived from climate simulations. And so the blue curve corresponds to simulation with in which anthropogenic sources are absent, whereas the red curve corresponds to the simulation fed with the observed greenhouse gas concentrations. So the curve corresponds to the average of about 40 simulations performed in different research centers worldwide, and the envelope indicates intermodal distortion. So it can be seen that only simulations integrating anthropogenic emissions of greenhouse gas and also anthropogenic air source are able to reproduce here the observations demonstrating the role of human activities in global warming. And it is indeed observed that during this period, the CO2 concentration increased from about 300 to about 370 parts per million. And this concentration is measured at the Mauna Loa reference station in the middle of the equatorial Pacific, away from any local sources. And in 2020, it is about 414 parts per million. So we have to keep in mind that in the last 400,000 years and before the industrial era, the CO2 concentration oscillated between 180 and 300 parts per million, following the Milankovitch cycle of about 100,000 years. So there is a clear departure from this, I would say, natural CO2 concentration variability. So how this will evolve in the future? So the way this is going to evolve is not strictly foreseeable, since the trajectory will largely depend on the actions that the nations of the planet will take to reduce greenhouse gas emissions. So this time we feed climate models with greenhouse gas concentrations that are no longer observed, but that come from scenarios which are produced using demographic and socioeconomic assumptions, and they are converted into greenhouse gas emission. So it is customary not to consider one, but several scenarios. And in the figure here, the greenhouse gas, so it shows the greenhouse gas emissions for the 4 scenarios adopted for the last IPCC report. And so the scenarios include emissions or concentration of pollutants, so in addition to greenhouse gas emissions, but also land use inventories and socioeconomic data, which are needed to calculate the impact of climate change. And in the last IPCC report, so these scenarios are named representative concentration pathways, referred here as RCP. And these scenarios have been translated in terms of radiative forcing, which quantifies the modification of the radiative balance of the planet, which is expressed in watt per square meters. And so the higher this value, the more the Earth atmosphere system gains energy and warms up. And so the four scenarios range from 2.6 watt per square meters to 8.5 watt per square meters. And so this figure shows the change in global average temperature at the Earth's surface compared to the end of the 20th century for three of the four scenarios just presented. And so the curves diverge from the beginning of the 21st century. And in red, so we have the most pessimistic scenario, that is, unfortunately, I would say the one that best reflects the current situation. In blue, the scenario to limit global warming below 2 degrees C, and in yellow, I would say the most optimistic intermediate scenario. So depending on the scenario, the warming could be between typically 1 to 4 degrees on average. So the 2 degrees C limit of acceptable, I would say, global warming was set in Copenhagen at the COP15 in 2009, and was at the center of the negotiations that led to the Paris Agreement. Caution encourages to respect this limit, proposed with reference to a period of the past when this average temperature had been reached without a climatic disaster. It is not an absolute limit, an absolute value, but if exceeded, would probably increase the risk of a climate bifurcation with potentially dramatic consequences. So Article 2 of the Paris Agreement expresses the commitment of parties to maintain the increase in global average temperature well below 2 degrees C, well below 2 degrees C above pre-industrial levels, and to pursue efforts to limit increase in temperature to 1.5 degrees C, as it would significantly reduce the risks and effects of climate change. And these thresholds have been discussed in terms of risks. The threshold of 1.5 degrees C corresponds to a reduction of 45% of CO2 emissions by 2030, and the threshold of 2 degrees C, a decrease of 20%, So, for example, here, in terms of water stress, an additional 500 million people would be at risk of water shortages. Almost 3 times more people would be affected by floods, while the fish stock would dramatically decrease. So in order to achieve the long-term temperature goal set out in Article 2, the parties strive to in Article 4 to achieve a global peak in greenhouse gas emissions as quickly as possible and reach carbon neutrality in the second half of this century. So until 1970, about 1,000 gigaton of CO2 were emitted, and it doubled in over the next 40 years. So the total, I would say, today the emission rate is around 40 gigaton of CO2 per year. So the figure here represents the global average temperature change as a function of the cumulative anthropogenic CO2 concentration since the pre-industrial era. So we see that this is a quasi-linear relation. There is a quasi-linear relationship between these two variables and framed by an envelope reflecting the uncertainty of this relationship between the models. So this is called what we call the climate sensitivity. And so this figure shows this other figure shows the emission reduction between 2050 and 2010 needed to ensure compatibility with the emission scenarios. And so in order to remain below 2 degrees C of global warming, the total cumulative anthropogenic CO2 concentration should not exceed 3,000 gigaton. And so taking into account, and for this, we see that to comply with this threshold here, we see that we should reduce by about 50%. We should reduce by 50% our greenhouse gas emission in 2050 with respect to 2010 levels. So if we take into account the uncertainty of the cumulative CO2 emissions for each scenario, it appears that the emission scenarios making it possible to limit global warming to less than 2 degrees C this century are characterized by a reduction in greenhouse gas by 40 to 70% in 2050 compared to 2010. So, and we should reach neutral carbon neutrality in 2100, or at least between 2050 and 2100. So now consider the carbon budget for the 2 degrees C global warming limit. So until 2011, approximately 1,900 gigaton of CO2 were released. And so the right to emit until the 2 degrees C limit is about 1,010 gigaton, as we should not exceed about 3,000 gigaton in total, as discussed before. So at the COP21, all nations were required to submit national targets for reducing greenhouse gas emissions, referred as nationally determined contributions, or NDCs. And so given the NDCs, the remaining budget in 2030 would be 220 gigaton of CO2. And so at the current rate, it would be reached in 25 years, which is tomorrow, I would say even today, at the timescale of public policies and energy strategies. And the energy sector accounts for 35% of greenhouse gas emissions, which includes not 25% for energy production, electricity and heat production, and 10% for other energy. So reducing our greenhouse gas emissions to mitigate climate change necessarily means a profound transformation of the system of production and distribution of energy production, and a revolution in our behavior in energy consumption. So in order to mitigate climate change in the energy sector, we have to make a transition towards low carbon energy supply technologies, among those the renewable energy sources, on which I will focus my talk, as they are intermittent and depending on climate variability. Nuclear, I would say, energy will be in depth addressed in future talks. So in the 1990s, Yuichi Kaya, a Japanese economist who wanted to identify the parameters that are determining for emissions of greenhouse gas in the atmosphere, and especially carbon dioxide, derived an equation linking demographic, economic, and energy parameters. So here through the population, through the gross domestic products per capita, which measures the wealth production carried out by the economic agent, through the energy intensity of the economy, that measures the energy efficiency of an economy. So high energy intensity corresponds to a greedy energy economy for a given level of gross domestic product. And through the carbon content of the energy, which is the amount of CO2 that must be emitted to have a given amount of energy. Here, TOE stands for a ton of oil equivalent. It was just, for me, a way to represent the energy here. So this equation is used to analyze or simulate the evolution of global CO2 emissions as part of climate change mitigation policies. So to keep global warming below 2 degrees C, it is necessary, so here, as was discussed before, we have to divide by 2 CO2 emissions by 2050. So we can use the Kaya equations to see what this goal imposes on the other factors of the equation. So prospective reports on the world population of the United Nations give a range of demographic change between 2010 and 2050, with a median scenario showing an increase of 35%. The economic growth scenarios are often published over a relatively short period of time, a few years, because the uncertainty is growing rapidly, as we saw, for example, in 2020, which was not expected due to the COVID situation. But nevertheless, there are a few existing prospective reports which point to the growth trend around 3% a year which would lead an increase in the energy intensity of the economy of 220%. And if we finally look at the energy intensity of the economy, so the overall trend is rather bearish. It dropped by 60% between 1950 and 2010, or about 10% per decade. And if this pace continues, we're entitled to expect a 40% decrease, but the prospective reports give a 50% decrease, which is so here. And so if we combine all these numbers, we see that we need to, so all this means that the carbon content of the energy must decrease by 75% in 40 years, which is, of course, which reflects the magnitude of the challenge that needs to be addressed in terms of energy transition. And that's it. So to understand the issues, of course, it is important to bear in mind the carbon footprint of energy production system. So the table here shows the carbon footprint of energy supply systems from the latest IPCC report, expressed so in a gram of CO2 equivalent per kilowatt hour. And so the low carbon technologies have a much lower carbon footprint than fossil energy technologies. And here, as an example, the photovoltaic technologies are nearly 10 times less emitting than gas. And among the so-called low-carbon technology, it is usual to distinguish nuclear energy from renewable energies. And so here, at least for this presentation, I will focus on renewable energies only, but once again, we will have many talks on nuclear. So when we talk about energy production, we must also include the load factor, which is a fraction, which is the fraction of time an energy supply system produces at its rated power. And so the figure here gives, in the form of box plots, the values of the load factors for different technology in the US. And it can be seen, for example, that the nuclear or coal plants have typical load factors of the order of 90%. That means that they produce at their nominal level 90% of the time. So typically, photovoltaic production has load factors of the order of 20%, which corresponds to about 25% of the load factor of nuclear and coal power plants. Wind and tidal energy have load factors of the order of 40%, with nevertheless a high variability, which correspond to about 50% of the load factor of nuclear and coal power plants. So compared to solar photovoltaic production, concentration solar power includes heat storage that doubles the load factor. So in conclusion, compared to nuclear or fossil production, it is necessary to install 2 to 4 times more renewable energy production capacity to produce the same amount of energy, which has the effect of impacting the surface required to produce a given energy. So another concept that is fundamental to have in mind is the concept of power density of electricity production, so which is the amount of power of the physical system per unit surface, per surface unit, sorry. And so the median values reported in this study give for nuclear a little over 250 watts per square meters, for coal about 120 watts per square meters, and for solar about 7 watts per square meters, and for wind power about 3 watts per square meters. So the power density ratio between nuclear and solar, for example, is about 35, whereas it's about 100 for wind. So therefore, for a given produced energy, wind technology requires twice as much installed capacity with respect to the load factor, and thus nearly 200 times more surface area with respect to nuclear and coal. So finally, to imagine scenarios of energy mix to reduce...
5 more minutes for your talk, okay?
Yeah, but that should be good. Finally, to imagine scenarios of energy mix to reduce greenhouse gas emissions without negative impacts induced from energy, environmental, and social economic point of view is far from simple, and this reflects the systemic complexity of the energy system. So we could reduce the energy transition to a constraint optimization problem, and so it is a very partial vision that largely forgets the human factor, but nevertheless, it can be illustrative. So the electricity grid must check the supply-demand balance at every moment. The demand is D and the production is P. The production is divided into several terms. So the production of renewable energy, PRES, the nuclear production, the thermal production, the imported or exported production, and the stored production or energy storage. So the major difficulty for a network operator is to be able to ensure the demand-supply balance at each moment with a variable consumption, but especially a production which becomes more and more variable and intermittent as the fraction of renewable energies in the energy mix increases. So another way of looking at things is to define the controllable energy production system as a service rendered to the grid to balance the energy, the net energy demand, defined as the difference between here the demand and the renewable energy production. So two objectives must be sought. The first aims to maximizing the penetration of renewable energies to minimize the carbon footprint of energy production. So here we do not discuss, we do not, it's not the production that we maximize, but the penetration, which is the ratio of production to consumption in order to take into account the consumption of this production. And the second objective is to minimize the variability of the penetration in order to maximize the grid stability, to minimize the costs incurred by the commissioning of controllable energy production systems, such as thermal power plants, for example. So now let's take a simple example that can be treated analytically and in which we replace the first objective with a constraint. So the constraint here is the energy production, which by construction equals the demand, is fixed, which amounts to ignoring the goal of maximizing penetration. And so the remaining objective is the minimization of the variability of the production, the consumption being fixed. So the previous equation are simply rewritten as follows. So the constraint one says that the sum of renewable energy production, here solar PV and wind, is equal to a fixed consumption. The objective of minimizing the variability requires the covariance matrix to compute, being computed between the load factors, here, eta PV, of wind and photovoltaic production. So by neglecting the correlations between solar and wind production, so the total variance is here written as the sum of the variance of renewable production, each written as the square of the installed capacity WP, and multiplied by the variance of the load factor. So by applying the Lagrange multiplier method, we can rewrite the system of equations for production variance into another system of three equations where lambda is the Lagrange multiplier. So now let's apply this equation system to the French energy system. So the table summarizes the year 2015, so the wind and solar production. Here are the installed capacities that we will try to find with the model, and the standard deviation of the load factor of each technology. So by solving the system of the three previously derived equations, we obtain the solutions for the installed capacity of the two technologies, which depend on the expectation and the variance of the load factors and the total desired production. So if we use the table, we can calculate here the sum of the wind and photovoltaic production, which was about 30 terawatt-hour. And if we compare now, so if we apply these two equations, we obtain an installed capacity for the wind of 9.5 gigawatt and for the photovoltaic of 4.8. And so if we compare to the actual installed capacity, where it works quite well, I would say, for a rather simple model. So now let's play a game together. Let's apply this simple model to two scenarios relevant to the French context. The first scenario is an electrical mix with a 50% nuclear share, which is a part of our pluriannual energy programming law that imposes this objective by 2035. And the second scenario aims to move the urban automobile fleet from thermal to all electric, with, of course, an electricity supply of renewable origin. So now, moving 72% of nuclear energy to 50% is tantamount to asking renewable to produce an additional 132 terawatt hour over 1 year. And so if we apply the solutions of the model, we have we obtain an installed capacity for wind turbines of 42 gigawatt, and for photovoltaic 22 gigawatt additional. Okay, so this is this corresponds to 4 times and 5 times the installed capacity of 2050. And so if we consider the rate of deployment, the actual rate of deployment, definitely we are not able to achieve the goals of the pluriannual energy programming law, which imposes an additional 30 gigawatt in 2035. Of course, this analysis is too simple. It considers only 2 alternative technologies to nuclear, but it allows to measure the efforts to be made to comply with the national strategies. Passing the urban fleet to 100 electric translates as follows. So the transport accounts for about 30% of final energy consumption, or 523 terawatt hour. Urban transport represents 1/3 of transport, or 128 thermal energy. And so moving from a thermal engine to an electric engine, provided that the source of electricity is renewable, so we can multiply efficiency by 3. Indeed, the efficiency of a heat engine is typically that of a Rankine or Carnot cycle, so about 30%, and the efficiency of the batteries is of the order of 90%. So if we multiply by 3 the efficiency, it allows to divide by 3 the need for electric energy, therefore 47 terawatt hour. And so if we now apply our small model, so this is the energy that should be fulfilled by renewable energy, then we obtain installed capacity for the wind of 15 gigawatt, and for the photovoltaic of 8 gigawatt, which are...
Can you conclude?
Yes, I have final slides now, which is about 1.5 the actual deployment here. So increasing the share of variable renewable energy production in the network is not simple. So it needs the sophistication of the network, which can be here divided into 4 phases. Phase 1, the low penetration of renewable is not an issue. In phase 2, the conventional control systems, such as thermal power plants and hydropower, are sufficient to integrate variable energies without having to transform the network. But after phase 3, investments need to be made to transform the network to make it smarter, more flexible, to manage the supply-demand balance with much more variable net energy demand. So just as an illustration, in France, we are here in 2017, so this is the share of wind and solar PV in generation here. And in our, let's say, national planning, we should reach 70% in 2030, which means by improving our network consequently. And with this, I thank you for your attention. And
yes, all right. Thank you, Philip. It's a coupling between the balance between the climate changes and how to cope with it. Very good, the start of overall theme. However, a time remained for the questions. Unfortunately, it was exhausted. So if you do have questions, please direct chat questions to him so that he can maybe chat back on the chat function, okay? So that we can preserve the rest of the time in the real Zoom conference, all right? So I hope it will work. All right, so the third speaker is gonna be Eric Rignall, who is a Donald Brent professor at UC Irvine, and he will talk about the impact of global warming on sea level, etc. Okay, Eric, please.
For forgot to mute myself. Can you see my slide and hear me?
Yes.
Okay, thank you. Thank you for inviting me, Toshi. Thank you for everyone to join this meeting. I'm going to talk about an impact of global warming on sea level. Several points I want to illustrate. It takes a long time to raise sea level, and it's going to take even longer to stop it. So I hope that this talk is a motivating effort for very strong action on the way we produce energy around the planet, but also to point out to you that from what we see happening in the ice sheets, having a clean energy production, it will not be enough to solve the problem. Antarctica has about 60 meters of global sea level rise equivalent locked in the ice sheet. Greenland about 7 meters, and all the 200,000 world glaciers and ice caps have about 0.5 meter. I will talk a little bit about the records from the past, show you what we know about the present, what the driving processes are and what it means for the future. And then I will talk a little bit about adaptation and mitigation of sea level rise. So we know from the polar record how the sea level varies with global temperature. Typically 20 meters of sea level rise per degree of warming of the planet. So if we consider that we're going to warm up the planet by 2 degrees or so, 2.5 degrees maybe by the end of the century, that means that the end state of sea level on the planet should be about 40 to 50 meters sea level rise, right? So we know that from the polar record. What we don't know from the polar record is how long it's going to take to get there. So right now the projection for 2100 is 1 meter, because we know it takes a long time to melt these ice sheets under a warmer climate. But the end state is not going to be 1 meter. The end state is several 10 meters of sea level. So we need to keep this in mind. Another important finding from the polar record is the rate of sea level rise. We know that there was an event about 14,000 years ago, which is called Meltwater Pulse 1A, where sea level rose about 4 meters per century for several centuries. Right? So this is not a model projection. This is not science fiction. It's something that happened in the past and is well recorded. And we don't know exactly how this happened. But this is caused by ice sheets, by the big ice sheets in the northern hemisphere and parts of Antarctica that decayed very rapidly during the deglaciation. To put things in perspective, 4 meters per century is the rate of sea level we would get if we were to speed up all the glaciers in Antarctica by a factor 8. Right? And it's possible to do that. We saw that in the wake of the collapse of ice shelves in the peninsula. We saw glaciers speeding by a factor 3 to 8. So if this was applied to the whole Antarctic, we would raise sea level by 4 meters per century. Right now, we are rising sea level 1 meter per century. But as a glaciologist, I'm worried about the possible runaway mechanism that could create these conditions for several meters of sea level rise per century. What this means for us is that we have much less time to adapt when the sea level rises so quickly. The traditional view we have on melt and how the models account for it is melt from the surface, melting of snow and ice. Ice has a lower albedo, and then you have water of the ice sheet makes even lower albedo. That's about half of the signal in Greenland. It's not the signal in Antarctica because there's not enough warming yet in Antarctica to melt the snow surface. There's also a concept out there that this water can reach the bed and speed up the ice towards the ocean. And we know from the past 20 years of research that this is not the case. This is just a little disruption on the main way that these ice sheets are decaying in the ocean. Antarctica looks like a white continent to the human eye, but if you apply radar imagery, you can see the flow of the ice from the continent into the glaciers and upstream here shown with bright colors, because that's where the ice is flowing fast. So these are the rivers of ice that discharge ice from the continent into the ocean. These rivers of ice play a fundamental role because you can change their speed under a warmer climate. And if their speed changes, I mentioned the case of glaciers in the peninsula speeding up by a factor 10, then you can have a very rapid rate of sea level rise, much faster than if you melt the surface. Melting the surface is a very slow process. You cannot speed it up as much as you want, but a glacier can flow much faster than what they do today. Typically today, the Antarctic glaciers are flowing 10 times slower than Greenland. So you could imagine that if the Antarctic was moved into a warmer climate like Greenland, the glaciers would flow considerably faster and raise sea level. Then the glaciers reach the ocean. They break into icebergs, which is my next slide. This iceberg here is 1 billion tons of ice. Greenland currently discharges twice the amount of ice that it should to maintain a state of mass balance. It discharges 200 of these icebergs every year. And to put things in context, only one of these icebergs would be sufficient to provide fresh water for a large city like Los Angeles or Moscow for 1 year. You would need one iceberg like this and melt it to provide all the fresh water you need. So there's a lot more ice, of course, in Greenland than that, but on the human scale, the loss of mass from these ice sheets is very, how fast the ice sheets are losing mass today. We know that from a satellite altimetry mission. We know that from comparing the amount of snowfall with how much is discharged by the glaciers. And we know it even better from gravity missions like the GRACE gravity mission that actually measures the change in mass of the ice sheets directly from the change in the gravity field. It does that for the Antarctic, for Greenland, and also for all of the world glaciers and ice cap, which would be extremely difficult to do with another means, whether it's field studies or airborne campaigns or altimetry. The gravity method is very spectacular for that. So you see these plots here that show how the mass is changing with time for Greenland, for Antarctica, and all of the world's glacier from GRACE. You see a map here showing in red where the mass loss is concentrated in these ice sheets. You see that it addresses all of Greenland, and in Antarctica, there's some sectors of West Antarctica and the peninsula, and some sectors of East Antarctica. You see that this curve of mass change are not linear. There's some curvature. That means that the mass loss is increasing with time. It's not a constant process. And if you extrapolate this rate over multiple decades, you see that we have about 80 centimeters of sea level rise by 2100 from all these ice sheets. And then you add thermal expansion to that. So we are currently proceeding at a meter per century sea level rise. There's going to be ups and downs, of course, in the climate system. So you need a long record for that. But the record that we have here, at least on this view graph, it's actually longer than that now, but is clearly illustrative of the trend. Now, to put that in the context of climate projection, this is an example here. You have these different scenarios of a low emission, mid emission, and high emission. And the black curve that you see over here is our current trajectory. And that's a little bit of a misleading aspect of IPCC, in my opinion, is that when we look at this climate projection, we tend to forget that we are currently on the curve of maximum rising temperature. We have not looked at a scenario where we could try to burn even more than what we do today to see what would happen. Right? The current trajectory of the Earth is on the worst case scenario of carbon emission. And we have these other scenarios by which we apply carbon emission restriction, but we are nowhere close to these scenarios right now. Right? So we should not forget about that. We are currently on the worst case scenario trajectory. Now, a big discovery of probably the last 20 years, looking at the ice sheets melting so quickly and in advance of what model projected, is that a driving process of the decay of these ice sheets is the ocean, and it's not something that was well represented in the models. Climate models for a long time have projected ice growth in Antarctica from a warmer climate because there's more evaporation from the ocean, more precipitation on the ice sheet, and not enough warming to melt the surface of the ice sheet. Therefore, Antarctica should be storing sea level rather than releasing sea level. Well, what observations show is that's not the case. Antarctica is losing mass, and it's losing mass at an accelerating rate. And the reason for that is that the glaciers are being attacked by warm water. That warm water is around Antarctica. It's always been around Antarctica. It's the Antarctic circumpolar current. It's been around for millions of years since the Drake Passage opened up. It's at depth, several hundred meters below the surface, so you won't see it at the surface. You have to dip instrument 700 meters below the surface. But it's circulating around the Antarctic in a clockwise fashion, pushed by the winds. And these winds have been strengthening with time. And because of the Coriolis force, they tend to push the surface waters to the north and the bottom water to the south. So more warm water gets to the Antarctic without warming the Antarctic circumpolar current itself. It's just the wind pattern changing and pushing the warm water more against the Antarctic than it did in the past. And this affects, of course, the parts of Antarctica that are closest to the sea, to the warm water, which is West Antarctica and the peninsula, and this sector of East Antarctica, which our Russian friends should be very familiar with because there's a few Soviet stations there, the Mirny station in particular, where there was a very active glaciology program in the 50s. I don't know exactly where it is now in Mirny, but this is one of the key areas in East Antarctica. This sector is close to the circumpolar water and has very vulnerable glaciers. So this warm water cuts the ice at the base. And this is the most efficient way to disturb the glaciers, because by removing that ice near the base, you remove all the basal friction, the resistance to the flow of the ice from frictioning on the ground, which is the main reason why the glaciers don't flow faster. So we directly remove the plug in front of the glaciers from this warm water very efficiently. And very few ice sheet models represent that process at present. Now, not all of this is new. There's also the theory of marine ice sheet instability that came out in the 50s and 60s and 70s by theoreticians, which shows that if you have an ice sheet resting on a bed that goes up in the inland direction, you have a stable configuration if you melt the ice. But if the ice sheet is resting on a bed that is sloping down in the inland direction, you have an unstable configuration, meaning if you start disrupting the glacier, it will keep retreating until it's a floating ice shelf. There's no stable state in between. If there's a bump in between, it will slow down the retreat. But if there's no bump, physics says you cannot keep this ice sheet stable. The only reason some of these parts with a downward sloping bed are still around today is that there are some ridges that block the ice here and there. So if this ice is liberated from these ridges, it will go into an unstoppable retreat. And the way climate is acting on these ice sheets is melting ice at the bottom from a warmer ocean and triggering instability of these glaciers. Okay, now where are the dangerous sectors in the ice sheets? I'll start with Greenland. We have on the right here, 3 large basins that are submarine, that have some retrograde slopes in them, but submarine means that if they retreat, the ocean will follow them and keep melting them at high rates. There's a 3 systems, the Jakobshavn, the Njergovsjas Fjord and Zachariastrom on the east, and then the Petermann Humboldt on the northwest. They contain about 2 meters of sea level rise. Jakobshavn lost its floating protection right now. It's retreating at 0.5 kilometer per year. Zachary Istrom lost its floating ice shelf and is retreating also at 0.5 kilometer per year. Nogafjords Fjord still has its buttressing ice shelf and is not retreating very much yet, but is melting under the action of a warmer ocean. And Petermann and Humboldt, Petermann lost a third of its ice shelf. Humboldt had a small ice shelf and lost it. These glaciers are retreating actually at 0.5 kilometer per year for Humboldt, which is a very high rate, right? 0.5 kilometer per year. So the floodgates of Greenland are opened up. We're not talking about the future. The protective barriers of these glaciers have been, for the most part, removed, and the glaciers are retreating down their marine basin. In Antarctica, we have a lot more floodgates. The most important one is the West Antarctic floodgate with Pine Island and Thwaites, which has a sea level rise equivalent of 1.2 meters. There are some very serious retrograde slopes in that basin. And right now, these glaciers have just a couple of ridges left before they go to a state of absolutely unstable retreat, meaning there's not an ice sheet model today that does not predict an unstoppable retreat past these ridges. The research right now is focusing on how long is it going to take to reach these ridges and what can we do to slow down the retreat once they get to these small ridges. There are also marine sectors in East Antarctica, and we tend to forget about East Antarctica. West Antarctica is lower, warmer, more vulnerable, but East Antarctica has also marine sectors, and some of them have a lot of sea level rise content. There's a lot of discussion about Totem Glacier right now, which has a 4-meter sea level rise equivalent, and Denman, which is close to the Mirny Soviet station, which has a 1.5 meter, as the deepest trough in the Antarctic. And we see the glacier retreating along that deep trough right now. So I label these with red is like the worst case, like these things are really on the way right now. They don't look spectacular, but the rates of retreat in Pine Island are 1 to 2 kilometers per year. This is very, very fast. The yellow are sectors that are changing. We see some indication of ongoing changes. They're not as strong as the red ones, but they are a concern for the future. And in the green areas, there's no indication that anything is changing right now. So the Pine Island Glacier Thwaites, I just mentioned it. This is an animation of the flow of these glaciers and the retreat. They contain 1.2 meter sea level rise. If they go down to sea, they will entrain the retreat of the whole West Antarctic ice sheet, and that's at least 3 meters of global sea level rise. Now, what we find in this sector is the glaciers are retreating at 1 kilometer per year, some of them at 2 kilometers per year, one of them at 3 kilometers per year. To put that in context, if we look at alpine glaciers, the glaciers that are closest to us, they retreat at kilometers per century. Right? If you walk in Swiss and on the trail, you will see a sign that indicates where the glacier used to stand at the beginning of the 20th century, and then you'll walk a few kilometers to find the glaciers now. In the Antarctic, we have actually the most rapid rates of glacial retreat on the face of the planet. Right? This is the coldest part of the continent, of the planet, and this is where we see the most rapid retreat of the glaciers. It's not in the alpine glaciers, it's not in Greenland, it's in this sector of Antarctica that we see rapid retreat. And a few kilometers per year is actually at the limit of what the models tolerate. The most aggressive ice sheet model that's been published in recent years is the Desconto and Pollard model, which put a limit on the retreat rate of the glaciers to 3 kilometers per year. They estimated it's difficult to conceive that the glaciers could retreat faster than that. We want to put a limit on the retreat rate of our glaciers. What we're seeing already now in 2020, glaciers in West Antarctica retreating at 3 kilometers per year. And this is just the beginning of the curve. We don't know in 40, 50 years from now how much the retreat rate could increase. We really don't know.
Eric, 5 minutes for your talk part. Okay?
Yeah. So today, 1 meter per century. Tomorrow, the possibility of 4 meters per century if a lot of these runaway processes start kicking. We haven't seen that yet. When they kicked in 14,000 years ago, there were no glaciologists looking at the record to document any of that. But the physical processes that acted back then are the same today. It's just different ice sheets, but the same physical processes. So in terms of our effort with sea level rise, there's the adaptation. I call it the ocean game. I call also this the Band-Aid solution, because it's not solving the problem. It's only working on adapting our coastline infrastructures to sea level, and it's going to be 1 meter for sure by the end of this century. It could be more if there's some runaway processes taking place in the second part of the century. Next view graph. Okay, sorry. Now, to put things in perspective, it takes 30, 50 years to put infrastructures in place. We know it's going to take some time for us to reach a zero carbon emission. It takes a while for the climate system to respond to that. Models show that it takes 30 to 40 years if you change our carbon emission. If we go to zero carbon emission today, it will only affect the climate 30, 40 years from now. The glaciers respond very quickly, and we found that Greenland and Antarctica they responded within 15 years of the point where the climate system clearly departed from the natural variation, which was about the 1980s. So what we do now is going to affect things in the ice sheets in 50 years. That's basic physics. And zeroing carbon emission is certainly a most important goal, but it will not be enough to prevent rapid sea level rise. It will not be enough to stabilize sea level at a reasonable amount. Now you might say, there's nothing wrong about raising sea level, except that humanity built everything, all its infrastructures, assuming that sea level would not change. So I like to make this analogy with Stone Age, that we didn't end Stone Age because we ran out of stone. We should end the greenhouse gas emission age because we found something better to burn. Adaptation is good. It's creating a lot of problems, but we really need a strong policy of mitigation. And I think this is what is being talked about today, mitigation efforts. I think what I wanted to emphasize is that the goal of reaching zero carbon emission is very important, is a must be. But as far as the ice sheets are concerned, this is not a satisfactory solution to end with a planet at 2 degrees above pre-industrial. It will not stop the melting of the ice sheets, and it will not prevent multiple meters of sea level rise down the line. Thank you very much. Oh, I cannot hear you, Toshi. Maybe you're muted.
Thank you very much. Well, it is alarming scientific facts. Thank you from Eric. Nonetheless, we have to confront the fact first, and then we have to figure out what to do, right?
Yeah.
Okay. Any questions from the audience? We have a few minutes to ask him or discuss. There are chats, maybe, but okay. So if a glacial solution is a slow issue, what is your advice? What to do?
You mean for energy production or for glaciological research?
Yeah.
Well, okay, so two aspects important to me. Glaciological research to understand what we don't know. There's a lot of work to do in the Antarctic, a lot of sectors that have not been surveyed, where we don't have ocean temperature and we don't know the seafloor depth. And we really need to have that for the models to operate. And there's a lot of unknown in East Antarctica, very close actually to, I was mentioning the Russian stations in East Antarctica. They are in strategic locations for that kind of work. In terms of energy production, I think it's really important to, as we discussed today, to look at a way to zero carbon emission. but it's equally important down the line to look at carbon sequestration strategy, because we already emitted too much carbon. We have to pay a price. We have to suck that carbon back, and it's going to be important down the line, and it's a little bit more challenging.
Okay, so that's different from a carbon emission issue, but you have to fix it. Okay,
yes.
That's a good point. Yeah, we have to.
And may I?
Sure, go ahead.
Yes. Okay, so your excellent presentation, coupled with the one previous about the permafrost thawing and releasing of methane, it looks like irreversible at this point. So carbon, if net zero is not quite enough, then have you considered net carbon negative strategies that we need to be put in place in time to reverse, to stop or reverse the process?
Yes, and I don't have. That's a good question, and I don't have the answer to that. I think the rationale is that if we curb our carbon emission, if we work on carbon sequestration, we can slow down the process. Stopping is a very difficult thing, but slowing it down, buying time for us is very important. If Thwaites Glacier retreats to the ridge in 200 years instead of 30 years, that's a very big difference for humanity. So quantifying that is challenging. The models that we have now are not quite able to tell you a definite answer. So my response to engineers is work as hard as you can. You will not waste your time. You will not waste your effort. And it will pay off. But let's be realistic too. It's not going to solve the problem if in 25 years we reach the fantastic goal of being zero carbon emission energy production. We will not actually be exactly zero, but it will be a huge step forward in slowing down the process. Stopping, you want to stop it? Well, you're going to have to pay a bigger price for that.
Okay, Eric, thank you very much.